So yeah, welcome all. Thank you all for being here. I will talk about my thesis, modeling the Zeeman effect in planetary atmospheric radiative transfer and applications that I've been working on for the last 3 years. Do I need a microphone? No, okay. So this is an overview. I have quite a few topics to cover, so I will skim a lot of details. I hope we can solve this in the discussion phase and the Q&A afterwards. I will begin with an introduction, introducing the basic terms and just the basic field in general. And then I will go on discussing some of the results of this work. Now, first question first, what is the point of this? There are plenty of instruments in measuring planetary atmospheres remotely, and in order to understand these measurements, you need to understand the radiative transfer. In order to understand the radiative transfer, you need software, radiative transfer software. So I've been modeling one aspect of this, which is called the Zeeman effect, which is how magnetic fields influence the spectroscopy of certain molecules and atoms in the atmosphere when we work with molecules. Now, this effect is important in Earth applications for temperature retrievals in the middle atmosphere, and it could also be used for retrieving magnetic fields, as I've been working on a bit as well. Yeah. So, first thing first, defining things. What is radiative transfer? This is the most basic pictures I could make of radiative transfer. You have some sort of incoming radiation, you have some interactions in the atmosphere, and you have some outgoing radiation. You can measure the end results. You have to model what goes on in the atmosphere in order to understand the physics of the atmosphere. And the things that influence the radiative transfer in the atmosphere, there's quite a lot. I've only worked on molecular spectroscopy, so this is all I will talk about. And in molecular spectroscopy, we can say that all molecules in the atmosphere and all molecules in general consist of several discrete energy levels, and transitions between these energy levels results in emission and absorption of radiation, and this is the basic physical process in the atmosphere. And as a picture of what goes on, and this is a bit messy, so start looking in the upper left corner. A transition between two energy levels give rise to a photon of some frequency. We call this central frequency of the line. And the concept in radiative transfer modeling is that we have some sort of absorption line with some frequency. Now, in the atmosphere, there is a lot of physics going on, so we will never just measure a single absorption line, we will measure some sort of line shape. And this line shape contains all the physical interactions with the radiation in the atmosphere, really. This, from the line, we can say, for instance, that the width of this line shape gives, for instance, the temperature in a very low pressure condition, or it can even be affected by other things. Now, of course, higher absorption means that less of the radiation gets transferred through the atmosphere, and so on and so forth. As one example of how a full radiative transfer process could look like, this is just a downwards looking satellite. So a satellite looking from the top of the atmosphere down, looking towards the ground of one absorption line, this particular case, a satellite looking down at Kiruna from space. And we see here on the x-axis, this is relative frequency, so the physics is involved in this process, and we see on the y-axis what is called the brightness temperature. This is a unit we use quite a lot when we talk about passive emission and radiation, passive radiative transfer, because it's very intuitive in very many circumstances. For instance, we can say from this that somewhere in the atmosphere, the temperature is 220 Kelvin. Somewhere in the atmosphere, it's 240, and so on and so forth. So it's just a way to turn radiation into a measure of temperature that can be intuitively understood. Now, to actually invert this to get the temperature from the radiation is a very, very long process requiring a lot of statistics. Now, the reason for this is because there are no perfect measurements, there are no perfect simulations. Everything is wrong in some sense. They're useful, but they're somehow wrong. In the model, to see this, we have to always understand how any physical property changes the radiation. And after the model, we also have to make assumption on how wrong is the measurement and how much can we trust our knowledge about the atmosphere. Now, the reason for this can perhaps be explained from this plot here, where this axis, the color bar is what's called the partial derivative, the weighting function of the Jacobian. It's a measure of how much the signal is affected by a certain altitude at a certain frequency. This is for the example before, I should say. And same frequency axis and then some altitude bins. Now, the white part is where the signal is from. So, as I said before, the temperature is 220 Kelvin somewhere. It's 220 Kelvin somewhere between 30 and 40 kilometers. That's basically what this plot is telling us. Now, and then we have to do a lot of statistical assumption in order to actually say, yeah, how certain can we be of the temperature in this range and so on and so forth, but I'm not going to go over that at all. Moving on to what I've worked on instead. Here is the first two papers that I've bundled together. They're about the modeling, not the applications. First one has the title, A Treatment of the Zeeman Effect Using Stokes Formalism and Its Implementation in the Atmospheric Radiative Transfer Simulator ARTS, which is the model I've been working on. The second one is an extension of the model called A Note on Modeling the Oxygen Spectral Cross-Section in the Atmospheric Radiative Transfer Simulator, where we combine the Zeeman effect with the limits in Earth's atmosphere. Now, what is the Zeeman effect? As I said before, it's how magnetic fields change the spectroscopy. The mental picture before of absorption that I showed you, or the picture I showed you of absorption, is that we have just one line, and the Zeeman effect, because of the magnetic field, changes how this line looks. The distance between splitting here you can call you can see as a strength of the magnetic field, and these are also polarized. I will not go over the details of this at all in this talk, but yeah, so there is some polarization involved in the radiation. And this is a simple picture of the most simple case of how this will look. It depends on the molecular configuration, so there are many, many different scenarios of how this will look like, and this is just a snapshot of just to show you that it can be a bit complicated at times. And what does this mean in brightness temperature? In brightness temperature, this is exactly the same example as before, looking down at Kiruna. In the wings of this line, nothing changes. It's in the center of this that things changes, and it changes quite dramatically from dipping as low as 210 Kelvin to actually staying at above 240. It means that we're sounding a different altitude of the atmosphere completely. And in the case of the statistics, this is what the Jacobians will look like. So, thank you, Matthias. And so, yeah, where we before peaked at around 80 kilometers at most, we here peak at around 50. And this is why the temperature is, or the brightness temperature is so much higher, because we changed absorption and transmission quite a lot. This is an example in the paper that we say that made us think that the model is actually working. This is a measurement by the Odin satellite in black, and the red curve shows the simulation with ARTS using the Zeeman module, and the blue curve shows the simulation in ARTS, saying that there's no Zeeman effect. And Odin is here observing at limb geometry. So in limb, you have your planet, and you're observing through the atmosphere, seeing space below, at the other side. And yeah, at 92 kilometers altitude, I think, somewhere over Turkey. Now, what is very important here is that if we were trying to actually use the blue curve to say what the temperature of the atmosphere is from this plot, we would get something that is completely ridiculous. We would get very, very strange temperatures. So it's very encouraging to us that the red curve fits so well with the Odin data, simulation taking ARTS Zeeman effect into account. Now, we did not do any fitting of temperature at all here, so this is just using standard atmospheric properties. We didn't actually try to make any determination of whether or not we're actually able to predict temperature there, but we were fairly confident after this that the model that had been developed seems to somewhat work. Now, moving on to other applications. This is for a ground-based sensor in Bern, Switzerland. Its title is Zeeman Effect in Atmospheric Molecular Oxygen Measured by Ground-Based Microwave Radiometry. And now, in this study, I provided the Zeeman module, and the people in Bern provided the sensor. Now, the temperature radiometer is the name of the instrument we used here, and it's a ground-based sensor in Bern, as I said. It has a turnable geometry or turnable optics, so it can observe in various directions. And it has a very, very high frequency resolution, a fairly good receiver, and it captures the molecular oxygen radiation from the mesosphere. Now, this is an example of measurement from the temperature radiometer, where, again, on the y-axis you see the brightness temperature, and on the x-axis you see the frequency around the line center. Now, as you see in the measurement, they're somewhat noisy, but this noise is very, very low, considering the fact that it's a kilohertz resolution in this figure. And yeah, this is a measurement, just an example of measurement. A very, very long integration time for this, so the brightness temperature is no longer as intuitive as in downwards looking geometry. Now, we compare this to ARTS for several azimuth angles. The reason why azimuth angles are interesting here, and azimuth angles means one azimuth keeping the same axis, pointing at a different direction, a different azimuth angle. The reason this is important is because at these angles, the angle between the radiation and the magnetic field locally will change, and this will change the polarization of the light. So we will see a small change in the signal because a large change in the polarization of the light. And we see this as the azimuth angles here in ARTS, where we have some change in the radiation, and we see that, yeah, not taking the Zeeman effect into account would be a bit silly as well here. And as well, on the right, we see the same thing. One big problem with this study, though, is that we have an offset on the brightness temperature axis here by almost 10 Kelvin between the two. We think this is because we wanted to test the Zeeman module here. We didn't want to use the line mixing module, which is necessary for lower atmospheric processes, and this will cause an offset. Sadly, we didn't do this. But when we compare the models after correcting for this effect, we see that, we see sort of the same effect. There's a bit difference in axis still, even after correcting. But we, most importantly, see that azimuthal behavior of the model and of the measurements are within the expected errors, meaning that we are emulating and actually predicting the change in polarization properly with a changing observational direction. Or at least this is the conclusion we drew from this. So yeah, this means that the measurements should be possible to use for retrieving mesospheric temperatures from ground if we first take into account the lower atmosphere in a better way. And most importantly for me, I think that it actually shows that the Zeeman model is somewhat working. What time is it? No, very good. Next paper. An Earth meteorological application. Title is Modeling the Zeeman Effect in High Altitude SSMIS Channels for Numerical Weather Prediction Profiles, where we are comparing a fast model and a line-by-line model. The fast model here is used by meteorological agencies. It's called ArcticTop. I'm not going to give you the name of that acronym because it's page long almost. And the line-by-line model is, of course, ARTS. SSMIS stands for Special Sensor Microwave Imager Sounder. It's an American sensor built by their Navy, the meteorological group at the American Navy. And it is part of the flight program, the F program, which has been flying for a very long time. So these sensors have been used quite a lot by meteorological agencies. Now, why is it interesting to compare these models? The problem for meteorological agencies is that they have to process a lot of data. A lot of data. There is many, many measurements all over the globe from satellites, many different satellites. And what they demand, therefore, is a very, very fast model. And this, in order to achieve a fast model, you have to make a lot of simplifications and parametrizations and ways to actually model this easier. And why is the Zeeman effect interesting in this case, and why is it interesting now? That's because numerical weather prediction people, the meteorological agencies, they want to increase the altitudes of their models. And to increase the altitude of their models, they need to retrieve data or radiation. They need to somehow constrain the temperature at high altitudes. The reason this is interesting is because there is some dynamical interaction and whatnot up there, not my field. But they want to increase the altitude, therefore they need to be able to retrieve temperature and other things at higher altitudes. And so, at lower altitudes, oxygen is a very useful molecule for this because it has a very stable signal. So if you want to use a similar instrument as you use for lower altitude, at higher altitude you would use oxygen, and therefore you need to take the SMN effect into account. That's the simple logic here. The SSMIS measurements are a bit different from how Tempera measures things. Where Tempera bins things in very, very narrow frequency bands, SSMIS bins things in very, very broad frequency bands and call them channels. What you see here in the bottom row is an example simulation of the brightness temperature as in the sky and the frequency binning or the channel width of one of the channels, channel 19 here. Everything within this bin and this bin is averaged together, and this is what they call a measurement. So it's a bit different from how the spectrometers work. Same here for different channels. And so these channels will measure at different altitude depending on where in the line shape they are measuring. Again, the ones binning things inside the line center, close to the line center, will measure high altitude, and the ones further out in the bins will measure lower down in the atmosphere. Just putting the SMN effect into context here, channel 22, which is the channel that has bins furthest from the line center, is pretty much not affected by the SMN effect at all. This is a comparison of turning on and off the SMN effect in ARTS. And this channel is pretty much not interesting from a SMN effect point of view. Channel 21, however, is very interesting. It actually has the strongest effect of all. And you see here a map of 1 day of data from, I think, end of August 2013. And yeah, the SMN effect for this channel is not very strong in the equator, but very strong over Siberia, Canada, and south of Australia. Now, the other two channels are also strongly affected. Sadly, meteorological profiles don't reach these altitudes yet, so we could not actually do any proper comparison between the models there. So I'm not going to talk about those at all here. And here is a comparison between model data from ARTITOV to SSMIS measurements for channel 21, same day, same data as before, and of ARTS and SSMIS. As you see, we have very, very noisy, it's not a very good agreement between the data and model. It's somewhat good, it's actually within the noise of the sensor, but there is clearly something more going on than just that. Problem, again, is that they're not very good at the higher altitudes as is today, because there is, again, a limitation in the constraints at the upper limit, and therefore your temperature gets worse, or temperature prediction gets worse. And we are using the meteorological atmospheres to actually predict this, the ones not taking this data into account. However, when we compare the models, we see that the two channels, or the two models, when we take into account just the model comparison, we see that the two channels agree fairly well. So it's the two models agree fairly well. So the only conclusion, or the strongest conclusion that and this is an important conclusion that we draw from this, that the models agree, first of all, within the uncertainty of the sensor, even though there is quite a large uncertainty there. And because the models agree so well, Met Office is going forward to actually implement this in the retrievals plan and increasing the top of the atmosphere. So a European agency will start increasing their temperature profiling to higher altitudes. They will start this summer, so I can't show any of those results. Here is some unpublished results that we're just continuing the work with SSMIS. We had already set up everything to simulate this in ARTS, so we wanted to also see, can we retrieve the temperatures ourselves? And this is the results we have for Kiruna, where we see the retrieved temperature profiles from a few years on the top, and modeled temperature profiles from average to modeling. It's called, the model is called MSIS, if people are aware of it. Now, the thin black lines we see over the top, the 12 kilometers here, that's the limit of where we don't consider ourselves sensitive to the measurements. So anything above is bad, anything below is bad when it comes to our retrievals. Things between is what we are influencing. The two things that are interesting about this, first of all, is the winter to summer comparison here, is that in winter the temperature is changing quite a lot. In the summer, temperature is not changing a lot, and it also agrees fairly well with model profiles. In winter, however, they change a lot, and the reason is this is from Kiruna. We're very close to the polar vortex, and this will change the middle atmospheric temperatures a fair bit. Yeah, one thing, as a somewhat joke that I find very funny from this, the temperature profiles don't change much in summer at all, meaning that the weather in Kiruna is boring somewhere. Before we can say more about this, though, we need to actually compare with other satellite retrievals. This is actually done, but I can't show you the data. I can show you the comparison because, well, licensing reasons. So I can't share any strong conclusions here. Now, the last part of my talk is what I said before, that the Zeeman effect is, of course, how spectroscopy changes by magnetic fields. And one application for this should therefore be to retrieve magnetic fields. And so these are two papers about doing that on Mars. The first one called A Method for Remote Sensing of Weak Planetary Magnetic Fields, where we show simulated applications on Mars. And the second one is called Martian Magnetism with Orbiting Sub-millimeter Sensor, where we simulate a full retrieval system. The last one is not published. It is submitted in the review, I think, was the last status. And so why is this interesting? Mars has a very different magnetic field from Earth. Here is one model of the Martian magnetic field from a guy called Kane and others in 2003. This is based from satellite data and then fitted to a certain model for the surface. Different models have different results, but this is one example. We see in average, that the magnetic field is very weak. I should say the numbers for Earth is about 50,000 in Kiruna, 70,000 is strongest, and the weakest on Earth is around 20,000 near the surface in Brazil. The strongest Martian magnetic fields, however, located in the south around here, are comparable to the weakest field on Earth. So there is still a strong field, but there is a lot of structure involved, whereas on Earth there is not a lot of structure, because we have a global magnetic field. Now, in the first paper, which I will not show any results from, we discussed the fact that if you know the polarized line shape, you can get the magnetic field back. Now, in the not published work, we were thinking, yeah, but that means we will need two sensors. We should have only one. So we tried to see if we can just use a single sensor to detect the same thing. And we did this by designing a measurement scheme. Here, an extraction from an orbit where observations are made, again, through the limb of Mars at various altitudes from these points. So the observations are like this. And the reason this is interesting is because we can observe from different, again, as a third paper, from different azimuth angles, and therefore we will get the polarization out from just these observations, and we could begin to determine the magnetic field without, a problem is that temperature will look sort of like the magnetic field in certain circumstances, wind will look as the magnetic field in certain circumstances, but if we can actually get the polarization out, wind and temperature will not look like that, so we will be able to get the magnetic field data. Now, this is how that example of measurements will look like in simulation. We will have at various tangent altitudes. Tangent altitude means that at the altitude above the surface. So 6 kilometers means that the signal goes above 6 kilometers at the deepest of the surface, and so on and so forth. And the brightness temperature again on the y-axis. And yeah, this will be a pseudo time series of all of these measurements. Now, Zooming in on the marked region, yeah, you can see the marked region. This is how one of these measurement blocks look like. And this is, again, the partial derivative of the Jacobian, the weighting function, what will you, for, in this case, the magnetic field. And so we see that in this particular simulation, we will have a sort of shift in the magnetic field. We're simulating this using circular polarization, which means it will behave like wind, sort of move the center of the line a bit, but not much. The thing that's very different here compared to Earth is that if we were to plot also the non-Zeeman-affected line shift here, we would have at most 1 Kelvin difference between this and the non-Zeeman-affected one, meaning that you wouldn't be able to see it on this axis. So it's a very small effect on Mars. It doesn't split the line per se as much as it broadens and shifts a slight bit. Setting up the retrieval system for all of this, here is some results. And on the left you see what's called a measurement response. If this is around unity, we say that we know that we can somehow understand the data, same as for the temperature retrievals I showed in the unpublished results. Here we see that the component that is east-west and the component that is north-south can be observed with this. As I said before, we are simulating this using circular polarization, and these are the ones that are actually affected by it. On the left, so we have a measurement response that's fairly good between 10 and 60 kilometers. And we have a fairly low sensor resolution. The reason it jumps back and forth like this is because we have an atmosphere that's gridded at 2 kilometers, and we're fitting a Gaussian to that. So very small difference will make a very big difference in how wide the Gaussian is, because they're on the limit of almost the model resolution in the atmosphere. Now, here are the errors plotted on the east-west and the north-south components, just for the same example as before in the observations. And we see that we will have around 150 nanotesla error around the 40-45 kilometers, a bit higher below, a bit higher above. Still good measurement response too. And just as an average for the two components, here is the estimated error for over the globe in the east-west component. Just between 10 kilometers and 70 kilometers, just the average number is around 180. It's the same for the south-north component, which is a bit worse because we don't, especially when we come to the poles, because we don't have very good, we're not very good at looking at these points from the north, nor these from the south. So we get a bit worse azimuthal resolution, so we get a higher error. And yeah, but the conclusions are that we should be able to retrieve the magnetic field of both these components at around 180 nanotesla. And that these numbers will be fairly independent every 4 or 5 kilometers. So if we make assumptions on that magnetic field being from the surface, for instance, we could probably get a better number, but we would have a worse vertical resolution. But that's it for my presentation, I think. So thank you.